Combinatorics, Lecture 13, Generating Functions. Let us start by recalling polynomials. Let k be one of the usual sets of numbers, integers, rational numbers, real numbers, or complex numbers. Or actually we can take as k any commutative unital ring. Recall that a polynomial with coefficients in k is an expression of the following form: a0 plus a1x plus and so on plus ak times x to the power k, where k is some non-negative integer and a0, a1 and so on ak are all elements in our set of numbers. So we can write it as a sum over all I from 0 to little k, ai times x to the power I. The set of all polynomials over our set of numbers k is usually denoted as k of x. This set has a natural structure of a vector space over k, which is given by the multiplication with scalars, which is done coefficient-wise, so lambda times the sum over I, ai x to the power I, equals the sum over I, the coefficient lambda times ai times x to the power I. And then we have the addition of elements, which is also done coefficient-wise. So the sum over I of ai times x to the power I plus the sum over j of bj times x to the power j is the sum over I. Now the index runs from 0 to the maximum of k and m are indices for the first polynomial and the second polynomial, the upper bounds. And then we just add coefficients ai plus bi times x to the power I. So whenever some coefficient is not mentioned, it is declared to be 0. So if m is greater than k, then am is defined to be 0. We remark that two polynomials are equal, provided that they have the same coefficients. So the sum over I from 0 to k ai x to the power I equals the sum over j from 0 to m bj x to the power j, if and only if each ai is equal to bi for all I between 0 and the maximum between k and m. So in particular, as soon as some coefficient is not defined, it is declared to be 0. If f of x is a polynomial, then the maximal k such that the coefficient of f at x to the power k is not 0 is called the degree of f. There is one particular polynomial where all coefficients are 0, the 0 polynomial, and then the degree of this 0 polynomial is not defined. And a very important property of the set of all polynomials is that they form a commutative associative algebra with respect to multiplication. So this multiplication is uniquely determined by the property that x to the power I times x to the power j is equal to x to the power I plus j, where I and j are non-negative integers, plus distributivity. And when we write the multiplication for the explicit expressions of polynomials, we get the following formula. The sum over I from 0 to k ai x to the power I times the sum over all j from 0 to m bj x to the power j equals the sum over all s from 0 to k plus m, and then x to the power s with the coefficient given by the sum over all t from 0 to s, at times b with the index s minus t. Now we generalize the notion of a polynomial to that of a formal power series. Definition: a formal power series with coefficients in our k is an expression of the following form: a0 plus a1x plus a2x squared plus and so on. This expression might be infinite, so we can write it as a sum over all I from 0 to infinity ai times x to the power I, where again all ai are elements in our set of numbers which we fix in our k. Remark: two formal power series with coefficients ai and with coefficients bi are equal, provided that the corresponding coefficients are equal, provided that ai is equal to bi for all I greater than or equal to 0. And the set of all formal power series over K is denoted very similarly to the set of all polynomials, but with double brackets. So it's K of x, the set of all formal power series over K with variable x. Note that each polynomial is a formal power series in the obvious way, so whenever the coefficient is not defined, it is declared to be 0. And in particular, this gives us a canonical inclusion of the set of all polynomials into the set of all power series. So polynomials are also power series where we only have finitely many coefficients which are not equal to 0. So they are finitary power series. Similarly to polynomials, we can define multiplication on power series. So formal power series over K form a commutative associative algebra with respect to the multiplication, which is defined by the same formula as for polynomials. We just delete the upper bound for the coefficient. So the sum over I from 0 to infinity ai times x to the power I times the sum over all j from 0 to infinity bj x to the power j is defined as the power series sum over all s from 0 to infinity x to the power s, and the coefficient at this x to the power s is given by the finite sum t from 0 to s at times b s minus t. And in particular, for this definition, we have that x to the power I times x to the power j is equal to x to the power I plus j for all ij non-negative integers. And we also have the infinite distributivity for such expressions. In particular, the canonical embedding of the polynomial algebra into the algebra of formal power series is an algebra homomorphism. So if our power series are polynomials, then multiplication just reduces to multiplication of polynomials. From this point of view, power series and polynomials look quite similar, but in fact, there are algebraic properties of these algebras which are quite different. For example, the polynomial 1 minus x is not an invertible element of the algebra of all polynomials. There is no polynomial which multiplied with 1 minus x gives 1. However, this element is invertible in the algebra of all formal power series. Here is a proof of this. So let us prove that 1 minus x times the power series in which all coefficients are 1 is equal to 1, regardless on which side we multiply. Well, the multiplication is clearly commutative, so it's enough to prove one of these equalities. So let's check the left equality. So to prove that 1 minus x times the sum over I x to the power I is equal to 1, we rewrite the left-hand side using distributivity. So we get the sum over I x to the power I minus x times the sum over I x to the power I. So the first summand remains as it is, and when we multiply with x, our index in I can be simply shifted by 1. So we get the sum over I from 0 to infinity x to the power I minus the sum over I from 1 to infinity x to the power I. And here we see that everything will cancel apart from the first term in the first summand, which gives us 1. And this completes the proof. Now we can define the notion of a generating function. So let A be a sequence of complex numbers. The ordinary generating function, which is denoted by GA, x, of the sequence A is defined as a formal power series, the sum over all I from 0 to infinity, AI times x to the power I. And another definition, the exponential generating function e of a, x of this sequence A is defined as a formal power series, the sum over all I from 0 to infinity, ai divided by I factorial x to the power I. So by definition, both the ordinary generating function and the exponential generating function of any sequence is a formal power series with complex coefficients because we look at sequences of complex numbers. clearly the maps which take as input a sequence of complex numbers and which output the ordinary generating function for the sequence or the exponential generating function for the sequence. Both these maps are bijections between the sets of all sequences and all formal power series. And it is very important to note that also we use the word functions. By definition, any kind of generating function of some sequence is just a formal power series, and there are no restrictions on any kind of convergence. So we don't say that it should converge to anything. We just define the generating function as a formal power series. If it happens that this formal power series converges to some function, then of course it's an interesting new piece of information which we can use to analyze the situation. So, if some formal power series converges in some neighborhood of zero, it is often convenient to realize this power series as a corresponding limit function. So here's an example. Consider the sequence ai is equal to 1 for all I greater than or equal to 0. Then the generating function for the sequence is the sum over all I from 0 to infinity x to the power I, and we know that this, by the formula for the sum of the geometric series, this is equal to 1 divided by 1 minus x, where x is close to 0. So this sequence converges to the function 1 divided by 1 minus x in some neighborhood of 0. So this is a generating function for our sequence. And the exponential generating function for the same sequence has the form sum over all I from 0 to infinity x to the power I divided by n factorial. And that exactly is e to the power x. So that's the exponential function of x. So in particular, we see that for the ordinary generating function, we get a function which converges in a small neighborhood of 0, while for the exponential generating function, we get a function which converges on all real line. This implies in particular that exponential generating functions usually have much better convergence properties. Informally, we can say that for ordinary generating functions, we compare our sequence with a constant sequence, while for the exponential generating functions, we compare our sequence with the sequence n factorial. And that sequence grows quite rapidly, so we can efficiently study sequences with much more rapid growth. We will often use a very special operator on the algebra formal power series, which is called the derivative operator or derivation. So definition: the map d over dx from formal power series to formal power series, defined in the following way, is called the derivative operator. So d over dx applied to the sum over all I from 0 to infinity ai times x to the power I is defined as the sum over all I from 0 to infinity ai times I times x to the power I minus 1. So this is the definition of the derivative operator on formal power series. So this operator has the following properties, just like the ordinary derivative. It is k-linear. It satisfies the Leibniz rule, which means that applying it to the product fg outputs the derivative of f times g plus f times the derivative of g. Moreover, if some formal power series converges to some nice function, and nice means that it is differentiable in some neighborhood of 0, then applying the derivative gives a formal power series that converges to the derivative of our function. So this allows us to use some analytic methods when working with sequences of complex numbers or even with integers, which is a discrete set, and then how do you apply analytic methods? But we can use generating functions to do that. Here is an example. Consider the sequence ai is equal to I for all I greater than or equal to 0. Then the ordinary generating function for this sequence is the sum over all I from 0 to infinity I times x to the power I. We can move x out to obtain x times the sum over all I from 0 to infinity I times x to the power I minus 1. But then we see that this sum is actually the derivative of the sum over all I from 0 to infinity x to the power I. We already know that the sum over all I from 0 to infinity x to the power I corresponds to the function 1 divided by 1 minus x. Therefore, the generating function of our original sequence is x times the derivative of 1 divided by 1 minus x. And this is equal to x divided by 1 minus x squared. So the ordinary generating function for the sequence ai is equal to I is x divided by 1 minus x squared. As for the exponential generating sequence for the same function, we get the sum over all I from 0 to infinity, I divided by I factorial times x to the power I. We can move x out and get sum over all I from 1 to infinity, 1 divided by I minus 1 factorial x to the power x minus 1, and this is equal to x times the exponent of x. So the exponential generating function for this sequence is x times the exponent of x. Another example. Let us determine the generating function for the sequence 1, 0, 1, 0, 1, 0, and so on. So in other words, ai is equal to 1 if I is even, and ai is equal to 0 if I is odd. So let g of a comma x be the corresponding generating function. Let us note that if we take g of a comma x and we add x times g of a comma x, this gives us a generating function for the sequence 1, 1, 1, 1, 1, and so on. So if we take our original sequence, multiply with x, which means that we shift it by one step to the right, and then we add it, we get 1, 1, 1, 1, 1, and so on. So the generating function for our sequence plus x times the generating function for our sequence gives us the generating function for the constant sequence 1, 1, 1, 1, 1, and we know that that is 1 divided by 1 minus x. In other words, 1 plus x times our generating function equals 1 divided by 1 minus x. This means that our generating function equals 1 divided by 1 plus x times 1 minus x. And this is 1 divided by 1 minus x squared. Here is an alternative proof of the same result. So we know that the generating function for our sequence by definition is equal to the sum over all I from 0 to infinity x to the power 2i, because the even components should be with coefficient 1 and all odd powers of x disappear. Let us replace x squared by y. Then we can write our sum over all I x to the power 2i as the sum over all I of y to the power I. But we know that the sum over all I of y to the power I is equal to y divided by 1 minus y. And now we substitute back that y is equal to x squared and get that 1 divided by 1 minus y is equal to 1 divided by 1 minus x squared. And so the generating function for the original sequence equals 1 divided by 1 minus x squared. Here is yet another example. Let us determine both the ordinary generating function and the exponential generating function for the sequence an given by n squared for n greater than or equal to 0. For the ordinary generating function, we want to understand the sum over all n squared times x to the power n. And we observe that n squared is a polynomial in n of degree 2, and every time we differentiate x to the power n, we get a factor of n appearing. So this suggests that we need to differentiate twice and maybe use some correction to compensate for the fact that x to the power n becomes x to the power n minus 1 after we differentiate. So we start from sum over all n x to the power n, and we know that this is equal to 1 divided by 1 minus x. We apply the derivative, and we get that the sum over all n n times x to the power n minus 1 is equal to 1 divided by 1 minus x squared. So the right-hand side here is the derivative of 1 divided by 1 minus x. Now, in order to compensate that our exponent at x is 1 smaller, let's multiply with x, and we get that the sum over all n from 0 to infinity, n times x to the power n, is equal to x divided by 1 minus x squared. We differentiate again, and we get that the sum over all n squared times x to the power n minus 1, is equal to 1 plus x divided by 1 minus x to the power 3. That's the derivative of x divided by 1 minus x squared. We multiply with x again, and we get that the sum over all n of n squared times x to the power n is equal to x times 1 plus x divided by 1 minus x cubed. This means that the generating function of our sequence n squared is equal to x times 1 plus x divided by 1 minus x to the power 3. Now let's look at the exponential generating function for the sequence. So we want to understand the sum over all n squared divided by n factorial times x to the power n. Let us write n squared as n times n minus 1 and then plus n. Then the exponential generating function for n squared equals the exponential generating function for n times n minus 1 plus the exponential generating function for n. And the second one we already know. To determine the exponential generating function for n times n minus 1, we want to understand the series sum over all n times n minus 1 divided by n factorial times x to the power n. We can rewrite it as a sum over all n, 1 divided by n minus 2 factorial x to the power n, which is x squared times the sum over all n, 1 divided by n factorial x to the power n. And this is x squared times the exponent of x. Since we already know that the exponential generating function for the sequence n is x times the exponent of x, we add them up and obtain that the exponential generating function for n squared is equal to x squared plus x times the exponent of x. Or we can write it as x times x plus 1 times the exponent of x. Let us also look at a finite sequence, at a sequence of binomial coefficients. So we fix a positive integer k and consider the sequence ai equals to k choose I for I between 0 and k, and ai is 0 if I is greater than k. Then the ordinary generating function for the sequence is equal to the sum over all I from 0 to k, should be k choose I x to the power I, which is equal to 1 plus x to the power k by the binomial formula. The exponential generating function for the sequence is equal to the sum over all I from 0 to k choose I, 1 divided by I factorial x to the power I. This is obviously a polynomial and it has a special name. If we change the variable from x to minus x, this is the so-called Laguerre polynomial, which is defined as a solution to a certain differential equation called Laguerre's differential equation. We can also go back from functions to sequences which these functions define. If we have a sufficiently nice function f of x, which we can represent by its Maclaurin series in some neighborhood of 0, so we write the series, so f of x is equal to the sum I from 0 to infinity, and then we have f upper I of 0 divided by I factorial x to the power I, where f upper I of x is the i's derivative of f of x. So we represent our function as a sum of its Maclaurin series in some neighborhood of 0. We assume that f can be represented in this way. Then we can say that this Maclaurin series, and this is a formal power series, and hence our function f as well, is the ordinary generating function for the sequence given by the coefficients. And the coefficients are ai, which is f upper I at 0 divided by I factorial. So this function represents the ordinary generating function for this sequence, as well as it represents the exponential generating function for the sequence f upper I at 0. So the same function, it gives the ordinary generating function for one sequence and the exponential generating function for another sequence. Example: let alpha be a non-integer real number. Let us determine which sequence has the ordinary generating function f of x given by 1 plus x to the power alpha. The first derivative is f prime of x. It is equal to alpha times 1 plus x to the power alpha minus 1. The second derivative, f2 prime of x, is alpha times alpha minus 1 times 1 plus x to the power alpha minus 2, and so on. The i's derivative will be f upper I of x, and it is given as alpha times alpha minus 1 times and so on times alpha minus I plus 1 times 1 plus x to the power alpha minus I. And if we evaluate this at x is equal to 0, we get that f upper I value at 0 is equal to alpha times alpha minus 1 times and so on times alpha minus I plus 1. And hence the sequence for which our 1 plus x to the power alpha is the ordinary generating function is the sequence ai, where I is greater than or equal to 0, given by ai is equal to alpha times alpha minus 1 times and so on times alpha minus I plus 1 divided by I factorial. And these numbers are sometimes called the generalized binomial coefficients. Some additional problems and questions at the end. Problem question 1. Prove that a formal power series is invertible if and only if the coefficient at 1 is not 0. Problem question 2. Check that both maps from sequences to ordinary generating functions and from sequences to exponential generating functions are k-linear. Problem question 3. Check with all details the Leibniz rule for the derivative operator on formal power series. Problem question 4. Determine both the ordinary and the exponential generating functions for the sequence given by ai is equal to I if I is even and ai is equal to 0 if I is odd. Problem question 5. Determine both the ordinary and the exponential generating functions for the sequence given by ai is equal to I to the power 3, where I is greater than or equal to 0. Thank you very much and see you next time.